Can you hear me? Okay. Sorry, John, I'm glad. It's just a little bit closer to my mouth, so maybe you will hear me breathe, but I can't really move it away. It's coming back. So, hello, good morning. I'm Ondro Mihályi, and I'm going to talk about Java and whether it's slow or fast and how it behaves in AWS Lambda. I will also say something about Lambda, so for those who don't know much about serverless functions and AWS Lambda, we will not jump into it, right? I will make you some introduction. First, I'd like to ask you if you have any questions. It will be easier for me to answer them at the end of the talk. If you go here to sly.do, type in the code GeeCON 2022, and at the end, if you send me some questions there, I will be able to read them, and we will not have to wait until people can tell me those questions. So please go to Slido, enter the code. Something about me. I'm a local Java programmer. I live in Prague, so I didn't have to travel very far to get here. But I'm never like a regular programmer. I'm also a lead of Java user group here. So I'll try to bring the community together under the Java user group, which is not funded by any commercial company. It's a community effort, and we like to keep it that way. I'm also a Java champion and committer to Jakarta EE specifications, so I have very close to Jakarta EE, and a lot of this talk will be also about, at least partially about Jakarta EE. And I'm a director at the Omnifish company, which I also co-founded. So that's shortly about me. If you want to talk about Jakarta EE or anything about Java, feel free to come after the talk. But now we will talk about AWS Lambda and how it works before we jump into how Java works on AWS Lambda. So basically, what is AWS Lambda? I show you here a life cycle of a Lambda invocation, but first what it is. Some people say that it's basically old CGI scripts in the cloud. It's actually not far from the truth. They behave similarly, or the idea is close to the CGI scripts, but it's like you were driving an old rusty bicycle back then in the 80s, 90s, and now you can drive a motorbike or a fresh new electric bicycle. So it's an idea, the same idea, but brought to another level, not only into the cloud, but it allows us infinitely scaling. So you don't execute your functions on your own computer and you still bound them to requests, basically. That's similar to CGI, because CGI was, you have a request on your server, execute a script, the script finishes, gives you some HTML, you send it back. But here, you can respond to events. You can respond to HTTP events from some HTTP servers, but you can also respond to events generated by messaging services or any service in the cloud, or even events created by yourself. So you can connect Lambdas together and let them run in background responding to events. So that's different. CGI only worked in HTTP servers, while Lambdas or functions in the clouds in general, there are not only Lambdas, but other cloud providers have their own services are similar to AWS Lambda. Functions allow us to deploy some code and execute it when it's needed. And what's also important, we don't have to pay for the code to be there and wait for events. As it's all in cloud, the cloud provider charges us for something. It's no longer our infrastructure, but they charge us only for the time we execute the code. So the code can lie there for free, and then when it's executed, the cloud provider charges us money, which is good for short-term actions that don't execute very often. It's good for actions which need to scale up and down frequently and almost unpredictably. It's not good for something that runs all the time, because then you don't have the advantage of running so-called CGI scripts when you need them, and it's more costly, because usually running things in Lambda or similar services is more expensive. The advantage is that if you don't run it all the time, then it gets less and less expensive. So now, what happens when Lambda gets an event? It needs to process the event. So according to the life cycle here on the slide, the cloud provider first needs to initialize the Lambda. So it has to initialize the whole environment it runs in, because even though it's code, it can't be just executed right away. Even for Java code, Java jar, you need a Java runtime, so you need to install it, or you would have to bundle it. But even for running a binary, you need an operating system. So that's what the cloud provider, in this case Amazon, does. It prepares everything. They even allow you to add additional services to it, like monitoring, which are together called extensions. So you can extend this runtime, this environment, and then also part of it is running your Lambda or your code until it's ready to serve requests or process events. So it also involves part of your code, even in this initialization phase. And then your Lambda is ready to process events. And in order not to repeat this initialization phase every time, Amazon keeps the Lambda warm. It means that it processes the request, but the process is still running, ready to be there, with no state. Or you can basically save the state in a static field, but no objects are preserved. So always when Amazon is going to execute the method that is processing the event, it will create a new object, call a method on that object, and then discard the object. So the only way to save some data persistently in your Lambda is to save it in a static field, and even in that is not predictable, because cloud provider Amazon can kill the Lambda. It can at any time, if it's not needed, if it's not used, it can at any time shut down the Lambda, and then it shuts down the extensions and the runtime, and it's not running anymore. And if there is a new event, it again needs to go from cold start, so it initializes everything, and then it's ready to execute your code. So there are drawbacks. Like every time your code is not needed for some longer time, you have to go again through this cold start, and that's what we'll talk about now. What is nice about these functions, especially in AWS, you basically pay only for your invocation of your methods, not even for the code that you write to start your Lambda, or basically everything in the static initializer is for free. Amazon gives it us for free. It only charges us when Amazon, and at the end, calls the method to process the event. And every time there is an event, only for processing the event, they will count the time, multiply it by some coefficient, which is from the CPU power we decided and memory we decided for that Lambda. So more power means more expensive, but it also means it probably will end faster. So you can sometimes save money when you choose more powerful Lambda. It finishes fast, and in the end, Amazon will charge you less. it's sometimes possible. But there are limitations. The limitation basically is that this only works in runtimes that Amazon provides us. And for Java, there are many other runtimes, but for Java, the only runtimes are Java 8 and Java 11. And they run on Corretto JVM provided by Amazon. So, in case we need Java 17, we need to use a custom runtime. We need to build our own runtime or choose some runtime that Amazon provides and build an extension on it. But again, that qualifies as a custom runtime. And sometimes, even if you don't need Java 17, you would like to use a different distribution or some custom runtime. For example, you can build on, since Java 9, it's possible to shrink your Java JVM and build your own small JVM that contains only classes and functionality needed by your application. So even for that, you would have to create a custom runtime. And the catch is, once you start using a custom runtime, so you say, I want a custom runtime, I don't want Java 11 or Java 8 runtime, then Amazon starts you charging for all the initialization. So now it's reversed. It no longer charges you for the code, for the static code that you execute within your function, but it also charges you for all the time it takes to prepare the environment, and that's not under your control. More or less, it's implied from your code, because, for example, if you have a big JVM and a lot of classes in your application, then the JVM itself starts longer. Or if your code is big and you have many resources, it needs to be unpacked from zip, so it takes some time. But you don't have that under control, and it's code. Some kind of part of code is executed by Amazon, a lot of it by you, because you can provide basically everything from scratch, from the OS level, everything on top. So that's the reason why they charge us, because it's not longer fully under control of Amazon. We can have a lot of customizations there, and it may take some time. But about cold starts with Java, specifically with Java. There's a clever guy on the internet who did, and he's not the only one, a lot of people measure how different languages behave, how AWS Lambda behave. But there's one guy who did this pretty recently, still 2 years old or 1.5 years old. So according to my contacts at Amazon, this may have changed since then, because Amazon is constantly improving the runtimes. But even those 2 years ago, Java was not that slow. Before, we thought, and there is a message that goes through the internet or the world, basically, everybody thought that Java is useless in Amazon Lambda because it's slow to start. But now one thing happened, that Amazon improved their support for Java. So all those native runtimes are tweaked to start faster. There are some Java optimizations in Java itself, so even if you use Java 17, you can enable some optimizations there. Or I saw some distributions, they are faster than others. But in general, Java is more or less on the same level, except C# and Docker are. For C#, I don't know why. It's a bit slower. Docker, yeah, you can imagine that's another abstraction, so it takes some time. So what it means is that we can be fast with Java. And now let's compare what Java can or what Java can't do. So if we think that Java, I'm not showing the screen, I'll need to change the settings. I want to show you something else than slides. This place. Okay. Okay, now you see it. Okay. So If you think that Java is application servers, probably not, because application servers have been around for a long time and there are other solutions. But let's say use an application server like Glassfish 7. I have an application which is very simple. It just contains a servlet, and the servlet, if you connect to the application, will just say something like hello world. So just to show you what it does, I'll start the application. It takes some time to load. You see it's not under 1 second. The slide promised, let's go back to the slide. The slide promised even 500 milliseconds or half a second, or even sometimes even faster. But we'll measure it. First, I'll show you so that you have an idea what the application does. This is the application. It just prints hello from Glassfish 7. But it's important how much time it takes from starting the JVM until the process can serve the first request. This is basically cold start plus first warm start. But usually also first warm start or first invocation from after the cold start takes a bit longer, because usually applications need to initialize something that can be used for further invocations of the method that handles the events. So let's measure everything together from start to serving first request. We'll stop the application, and there I have a script that just launches the application, gets the response, and stops the application and measures how long it took. So here, under these conditions, it's around 6 seconds. Let's no, where am I? Sorry. Let's record it here. I have a graph, a chart, just to show you comparisons and how much it takes or where we are on the journey to get to fast Java in AWS. Now to get a little bit faster, we can try embedded Glassfish, which is faster because it no longer needs to run all the administration console and some services. It does the same thing. If I kept it running, it would just show the hello world from embedded Glassfish. You see it here in the end. This is the response from Glassfish. And you see it's under 4 seconds. Not very good, but we have an improvement. Imagine that all the cold starts in Lambda would take 4 seconds. That would probably take a bit longer because I have a powerful computer, and in Lambda there's no equivalence to the computer, let's say. There is, but you have to ask Amazon to extend your quota. There is something like 2 CPU or 4 cores and 3 gigabytes of memory at the most you can get just without asking. But more or less it's comparable. If we get 4-second cold starts, what it means? We still have to wait once in a while. It depends how frequently our function is called. Once in a while we have a cold start because it wasn't run for 10-15 minutes. I think that's about the time after which Amazon usually shuts down not used Lambdas. So every 15 minutes or longer, if we only execute Lambda once in a while, we get this performance penalty. Users would have to wait for seconds. If we have a background job, that doesn't really matter because it's launched once an hour. It maybe takes 10 minutes to finish, so additional 4 seconds are fine. But if we handle UI, if you want to provide some JavaScript that runs on user's computer or mobile phone, then it's a huge difference. Another reason why Amazon would start a new Lambda with cold start is if there is already Lambda running to serve another request. So if you have parallel requests coming, imagine more people start coming to your page, to your site, and they use the Lambda, or they need to launch Lambda together in parallel. So every time a new Lambda is launched while the others are running, there is again a cold start because it's a new instance. Every new instance of Lambda in the pool of Lambdas, let's say, requires this cold start. And now we are at 4 seconds. Let's try with a very similar application based on Spring Boot. Now we're no longer fully Jakarta EE, but Spring Boot support, where is it? Here. Spring Boot supports servlets, so we can basically use the same code. Some people say that Spring is fast, some people say that it's slow. It really depends. It's faster, 2.5 seconds. It's faster than Glassfish, so we could say it's faster than Jakarta EE. But let's wait. I saw companies that evaluated Spring, even the Spring Cloud native support for AWS Lambda, and they said it's too slow for cold starts. We can't use it for everything. So you see now, 2.5 seconds is still not very good. And so that we can compare it with something else, we basically will see the number from my slide. If we just as a proof, we execute a very simple Java application, just an application that prints a message. It doesn't even start an HTTP listener, so it's not possible to measure it in the same way as before. So we measure just how long it takes to start. I'll launch it here again. So it's now 70 milliseconds. And we're around the numbers that we had on the slides. And you see, it's almost invisible. It's so faster than all the Spring Boot and Glassfish. So basically, if you just run Java without anything else, it actually contains something. It contains some AWS Lambda dependencies if you run it in Lambda. But if you run it with only what's necessary and you write all the code yourself, you can get very fast. Now the question is, can we get to something close to that with some additional help if we don't want to write everything, all the code ourselves? That would be like a holy grail of Java, to have all the toolings that we are used to, but have the speed that we didn't have with them. So now let's come to the slides. And ideally, because I have a Jakarta EE background, it would be good if it supports at least partially Jakarta EE, so it's not completely new. I know that a lot of you know other stuff, but I think it's also good if you at least know some part of Jakarta EE, because it is supported by many implementations and it's just there, everybody can use it. And the good news is there are at least 2 options to leverage the knowledge of Jakarta EE, at least part of it, and get very close to these numbers of plain Java application. One is the Quarkus framework. It's a framework introduced by Red Hat a couple of years ago, I think in 2019 or 18. And it builds on Jakarta EE and microprofile, mostly on microprofile, which builds on Jakarta EE or parts of Jakarta EE, and adds additional things like support for reactive programming with Vertex, and they have REST easy component from the JBoss application server, and which they also recreated or rewrote from scratch to support reactive programming with JAX-RS or REST. And they also recreated or rewrote dependency injection. And that's the key part of Quark. The dependency injection at the core is basically what is inside. It's not so much promoted as supersonic subatomic Java as they call it, but I think this is the core of Quarkus and how it works. Quarkus basically focuses on optimizations at build time. So a lot of things that Glassfish and Spring Boot do is reading annotations, reading configuration from either Java code that it has to be scanned, or from some configuration files. And all of that can be basically pre-compiled, prepared into binary code, into Java code or bytecode. That is no longer configurable, so if you launch the application, you can't configure it, you can't extend it, but it's fast, because you don't have to parse all this information. But during writing the code, you can do that. You write the code that contains annotations, that contains configuration, but at build time, everything is closely integrated together, even the dependency injection. So that's what I mean by core. Even Quarkus even scans annotations for dependency injection and injects bytecode in there. So no longer the dependency injection needs to work with annotations. It directly knows which classes or which object it should inject. Quarkus is quite big when we compare the ecosystem. It has a lot of plugins for many libraries. And why it's important is that these libraries, a lot of libraries, especially in Jakarta EE, rely on the reflection and reading annotations from classes. And these plugins basically allow Quarkus during build time to get this information and compile the code that provides the information to the libraries, so that the libraries don't have to scan all the annotations. They have everything in code. It supports imperative and reactive programming, as I mentioned before. And it also supports native compilation to GraalVM. Again, this kind of extends the idea of optimizations during build time, because for GraalVM, you basically need to create the GraalVM during build time. And GraalVM needs some things from your Java application. It limits what you can do in Java application. So Quarkus basically can inject the information or can gather the information during build time, provide the information needed to GraalVM, because GraalVM can do a lot more if it knows what it should add to the final binary. And then mostly things work. I'm saying mostly because I know from people who use native compilation, they often need to test again if the GraalVM binary works as normal Java applications. Sometimes it doesn't. But most of the time you get very fast binary. The drawback is it takes quite a lot of time to create the binary. So there's always some catch. Then another option is Piranha Cloud. It builds on a lot of components used by Glassfish, so it's more or less like Glassfish reinvented, but a lot of there is written from scratch. And basically the core is a bare bone and fast servlet container written from scratch, completely redesigned. It doesn't use class path or like class path hierarchy. It uses just flat class path. You just create a Java object and you can run a method to serve a request. Then on top of this servlet, you can either, a servlet container, you can either just deploy regular servlets, and then you rely on the servlet itself if it's fast or slow. But it also contains some components that you can use already, and they are packaged as Jakarta EE distributions. Not all Jakarta EEs provide it, but at least core profile is there, which is the smallest profile directed at microservice development, and then some specifications, and it's growing, and the target is to be able to run web profile applications and pass the web profile specification, testing kit. But it's also extremely modular to that extent that you can even run the servlet container without HTTP listener. So you can really create an object and call a service method with a request and get a response, and really work with it within the code, within your application, without going through the HTTP stack. And because of all this, it's basically plain Java. It doesn't have all the magic that Quarkus have, but the drawback is it doesn't support GraalVM compilation more than any other Java application. So you have to do all the work of adding libraries and any support for external libraries to run on GraalVM. And it also can do some optimizations during build time, but it is not focused on yet. So it can improve something. It focuses on optimized. It focuses on optimized code, optimized execution, but it's still plain old Java. While Quarkus really generates a lot of code to improve your own code or improve the existing frameworks. But so that I don't talk about slides, I'll show you how it basically looks. So I created a sample Quarkus application. And I want to show you basically not the code. The code is normal, more or less normal Jakarta EE or microprofile Java application, whatever. You can use also Quarkus own APIs. But what is nice, or what is really special, is where do I have it here? Is the outcome. And in this case, this is a function zip. So Quarkus already supports AWS Lambda in some way. It has a profile for that, and it can generate directly the zip file that you can upload to your Lambda configuration and update the Lambda code. You don't have to do additional work on your side. You just take the zip, upload it there. And what's interesting, I don't know if I can make it bigger, probably not, but I hope it's already quite big. Maybe zoom. Oh, yeah. So what's interesting is that if you look into the package itself, it contains some libraries for Quarkus, but a lot of them are small. And basically all of them are small. But what's also interesting, is your code is generated. And it has greeting lambda, which is your code, but there is additional greeting lambda bean class, which means this is the support for dependency injection. So dependency injection is basically now in your application. There's no framework that provides dependency injection. There's Quarkus, which builds the class, and the class itself provides dependency injection. So it knows what to inject and where it should get it from. There are other optimizations, like if you carefully check the dependencies, there are only things needed for Lambda, so you won't see any HTTP listener dependency there. There's no HTTP listener there, again. But it's the approach compared to Piranha Cloud is the other way. Like you create a code, you call a Quarkus plugin, and then Quarkus finds out what it needs and only adds what it needs. With Piranha, you build everything from scratch and you add the components you need, and you can selectively choose what you need, what you don't need, and you have better control of what's in the result, but it's also more work. With what is nice about Piranha, you can see what's happening there. So I showed you what Quarkus does in the end. And now I'd like to show you what, I'll turn off these zoom. How Piranha works. So Piranha works, as I said, from the bottom. There is a servlet container. You can deploy anything on top of it or add extensions to Piranha. And Piranha source code is basically the minimalistic Piranha source code looks like this. There is a main method. You create Piranha object, start it, and this is just to be able to demonstrate request and response cycle. But basically, what you do is you add your servlet class there. So you create it and directly add a servlet mapped to the root URL, and that's it. This is all the configuration, all you need. No HTTP listener at this time, just an engine that is extended by a servlet, which is a standard web servlet defined by Jakarta EE. It has a do-get method, does something based on the request, and types hello from Piranha Cloud. But this doesn't launch the HTTP listener. To launch an HTTP listener, I think I have it here. Yes. You can add a processor, HTTP web processor and default HTTP server, and add your Piranha engine to it. And this means it will route all the HTTP requests. It will basically create the HTTP servlet request object for you out of the incoming HTTP message. And then it will do the same thing that we did before. It will call the service method with a request, will take the response, and then unwrap the response object to an HTTP response and send it back. So this is how it's extensible and modularized. You can create your own HTTP server. You can provide. There are actually more HTTP server implementations. One of them based on Project Loom, the virtual threads, which requires Java 19 now with Project Loom enabled. But you can really play with it and exchange a lot of parts and implement a lot of parts if you don't like what's in the stock. So this is how Piranha works. And now to complement all our measurements, I will run Piranha, how fast it is to serve a request. And I have the script here. I could do this for Quarkus. We would have similar numbers. Maybe Quarkus will be a little bit, sorry, I'll open it here. Quarkus might be a bit slower because it already contains some things on top of servlet. I failed to connect. It's something running on. I think I left something running on the port. Okay, now it works. So it's 330 milliseconds. Now let's put it into the, here it is. Piranha. Okay, so hopefully you can see it. It grew a bit compared to plain Java, but it's still around half a second, even less. I want to remind, this is just a simple servlet. If you add more functionality, it will grow a bit. With Quarkus, you are at the starting line at around half a second. With Piranha, you can get on the same starting line with just adding JAX RS support for REST and dependency injection. But still, it's much faster than the previous approaches. Okay. But there are other options how you can optimize cold startup. It's not only choose a framework which suits better your needs, you can also play with some tweaks in JVM itself, or even choose a different JVM. Here is a chart that I did half a year ago, just for myself, so the numbers are not exact. Like I didn't measure everything thousands of times and pick the random and all the stuff. I measured everything around 5 times and just saw what is the average number. But it's quite reliable. If you compare the numbers, most of the configurations on the left, when I tried different configurations, didn't have much impact. Some of them made things even slower. But there were 2 things that stood out. And one is tired compilation, which is here on the third option. And it improved things slightly, but it's around 10%, not bad. What tired compilation means? Tired compilation means, or this option basically, it disables second level just-in-time compiler. Compiler works in multiple layers, or so first it focuses on very immediate things like low-hanging fruits. It discovers things that are fast to discover, it will optimize them. Usually it compiles short methods into inline code and things like that. And then in the second layer, after this is done, it will try to optimize more. And this is good in long run. If you want to run the Lambda for like 5 minutes, it's better to optimize everything in the beginning and during the Lambda invocation so that the code runs faster. But if you want to have a short cold start and Lambda doesn't run for a long time, then it's good to disable second level compiler and keep only the first layer. Just for curious, if you disable first layer compiler, it doesn't really help, because then the compiler doesn't run, which is faster, but the code itself is so not optimized that in the end, even for an application like this, you would have like over 1 second, almost 2 seconds startup, because it would be basically interpreting Java code, which is slow. And the second option that stood out is class data sharing. Class data sharing is basically a hack that, but it's supported by OpenJDK. It allows you to run your application once, collect information about all the classes that are loaded by the JVM, by your application, store information about all these classes, and next time you can point JVM to this stored information, and it will skip initialization of loading classes from the class path. It will have this information already, and it's a bit faster because it will skip all this class. I think it's even class loading. So it will have all the classes that it needs to be loaded. So it will load them directly using the metadata. It no longer needs to parse the metadata from the code. So with this, we could get, in my case, from around 800 milliseconds with a slightly more complicated application to 600 milliseconds. Another thing that stood out is I tried several Java versions. Sometimes Java 11 was faster, sometimes Java 17 was faster. But what was actually interesting, when I tried Zulu Java 17, I had much faster times, and I tried it multiple times. And you see it from all the others. They are faster. So all the other variations are faster than the others. I tried Corretto because that's the JVM used by Amazon Lambda natively. But I'm not saying that Zulu is the fastest JVM. But for this, maybe Zulu has some optimizations during startup. Maybe there are other JVMs that have the same optimizations. I don't know how they do it. It's just to point you, or to let you know that even changing the distribution, and now we have, I think, 10 or even more options, not only Oracle JDK, you can get faster startup times. And then there are further options. I mentioned faster JVM. either Java version or distribution. But you can simply even just increase the amount of CPU and RAM for the Lambda, and your Lambda would start faster. Sometimes when you really care about short cold starts, that's the simplest option. It's more costly, but it may pay off. Another option which is not supported by AWS Lambda but would be nice, and I think Google or Microsoft Azure already support it, is just boost your Lambda during cold start, so it gets more CPU power in the beginning, and then you pay normal price for the rest. So that's quite nice, because when you really need to shorten the cold start, you need to boost the power, and then you continue as if it was a warm start. AWS Lambda provides options like pre-warmed AWS Lambda instances, which is nice if you really want to avoid cold starts, but it's not 100% because it only pre-warms that amount of instances. But if you need more to run in parallel, you again need to suffer the cold start. And these pre-warm instances are costly because basically they run all the time. So to avoid these things, avoid paying more, you can use other options like custom JVM, which you can do with J-Link. I don't have time to show, but it's quite easy to integrate that into Maven, into CI, and basically the same way how you build your application, you can build your own JVM tailored just for your application, and then run it with a script, and this can save some milliseconds because there are much less classes in the final JVM. And then what is quite drastic, but also most significantly decreases cold start is building a native binary out of your Java code. And this is possible with GraalVM, and Quarkus provides integrations and makes it very easy to do. So with this, you can really get to the startup times of like shell script or any shell commands, because it basically creates like binary like with C. And yeah, that's basically all the options. Then there is one more option on the horizon, which is called CRAC, like some people say crack, Java on crack. But it's short for, I think, coordinating restore and checkpoint or something like that. So basically, similar to CDS, but you don't store the information about classes. You store information about the whole JVM, all the objects that are created. It won't store the connections because you have to recreate the connections. That's why it's coordinated. You have to support it in your application. You have to be able to restore some resources that are not able to be saved on the disk. But all the other stuff, mostly the memory, all the structure, basically the point in time when your application is ready to serve requests can be stored to disk and then start immediately. No, it would be even faster than CDS because it basically run from that point. Like if you hibernate the computer and then you open the computer, there's very slow delay. But that's still not there. I think Azul has some working version, and it's going to be in OpenJDK, but we'll see when. Actually, GraalVM support or something like that is also planned to be in the OpenJDK in some time in the future. It was announced, I think, 2 weeks ago at Java 1. So we have a lot of things to wait for. I think I used my time, so if you have any questions, I think that's basically it. We'll check Slido if there are questions. Oh, there are quite a few. So how does the code from developer ID gets through testing before it gets into prod Lambda? Also, the dev code is stored in JIT or alternative VCS. So, yeah, that's a tricky question. First, you normally should test the code yourself on your own machine. It might be easier or even less expensive to use AWS Lambda for each developer because it's really easy to create an AWS account for each developer and then create a Lambda. You can just, if you use CDK like I used here, you just launch this script. CDK is nice because it supports Java and many other languages, but if you write code in Java, you can also define how the Lambda should be created in Java, and then run it. It will use your AWS account, it will create everything, and then you can run it. And this is a way how to test things in the near production environment. If you want to just run the code like unit test, integration test, you can still do that on your own. But it's tricky to do some component testing or system testing because you need a lot of services from the cloud, and this is not really easy to connect to from your computer. So how the AWS knows that init step has completed? Oh, does it use some health check for it? It knows because it's AWS who runs your code in the invoke function. So it's not that you do something. You just prepare a method. I didn't go into details. I will show you basically how the function looks like. So I'll have more time to show. Okay, here's function up. So this is an example of function code. And it's basically just a class that implements an interface. And Amazon libraries find this class, or you basically give them instructions where to find it, so full name of your class, and it will call the handler. It will just call the method. So the only code that is executed when the event comes is this. And you get the event information here, and you output response to Amazon here. So it's just a single method. But you don't call it from your code. It's AWS who calls the code. So basically, AWS just adds your code to the class path. It launches JVM, and then it loads your class and executes the method. And the side effect is then you can do something here before Amazon runs the method. But it's not intended. Like Amazon supports that. They don't say you shouldn't do it, but it's not like they would build the solution to do this. It's just natural in Java. They load the class. At that time, the static initializing code can be started. So you can initialize everything here. For example, for Piranha, you would create the container, configure it as a servlet here, so that everything is prepared when the method is called. A method would just delegate to Piranha, and that's it. So this is how Amazon does it. They control everything, so they know. Once your JVM is loaded, once they can call or load the class, then they call the method. And next time, it's again the code of AWS, Amazon code, that will just create the request or event object, and will call your method again. So this is how it works. I don't know how much time we have. Do we still have some time for questions? Maybe if you have more questions, come here. I also have some T-shirts. So if you come here and talk to me about these things, even those people who I already answered the questions, can come here and I will give you a T-shirt. I don't have that many, but come and I'd like to talk more. So maybe one more question to answer. Hey, how AWS knows that init step has, oh, that was already. Would you optimize the Spring Boot application with Quarkus? Would you optimize the Spring Boot application with Quarkus Piranha Cloud for AWS EC2 cluster? Would it improve overall speed? Okay, I don't really understand this question because Lambda has nothing to do with an EC2 cluster. Of course, it probably runs some EC2 on some EC2 instance, but it's completely transparent. So you could just combine a Spring Boot application running on EC2 and talk to or send events to a Lambda written in Piranha or Cloud or Quarkus, so that you have multiple components of your application, and that's natural in the cloud. Even with functions, with Lambdas, you would have more of them usually. And you don't have to use Lambda for all of your pieces. Sometimes it's okay to run something that runs longer on an EC2 instance. I heard some people also use Fargate as somehow as serverless. They launch Fargate Docker instance when they need it. It takes longer. It's usually like 30 seconds to launch the Docker instance, but then they are ready to serve requests. And there you can use anything because 30 seconds, 35 seconds is not a big difference. So the difference is basically in Lambda. Okay, so we'll answer other questions if you come here or in the corridor somewhere. Catch me, I'll be here all day. So thank you very much. Have a nice day.